So my name is Pierre Walker. In the Teams chat there is Andrés Riedemann. And as the slide shows, we also have a third collaborator who is all the way in Malaysia, Hanwha Yu. And today, on behalf of all the developers of Clapeyron, I'll be presenting to you our little package, which is intended for equation state modeling within Julia. Now, for a bit of motivation behind why we developed this package, implementations of equation states have historically been a black box, being only available in commercial software such as Aspen and gproms, or internal lab codes. However, in recent years, this has been changing, with packages such as CoolProp and Thermo really leading the way with more simple formatting models. And today there are now more modern and advanced packages such as Theos and TechB. And it is within this realm Clapeyron really led the way here when it came to providing these open source advanced equations to state. Now, as a bit of a background as to what equation states are used for, these models are vital tools within a chemical engineer's arsenal. They have historically been used to model oil and gas systems, with more recent applications involving carbon capture, where people might be interested in modeling the vapor-liquid equilibria, obtaining bulk properties such as heat capacities, or even predicting asphaltene formation. However, more recently, people have used it to model much more complicated systems, such as polymers, where I myself have used it to model polymer demixing. There's also been applications in electrolytes and brines, where we can predict osmotic coefficients, the precipitation of salts, and gas solubilities in the presence of salts. Now, and one more application is also in predicting the solubility of pharmaceuticals, which has been quite a great interest within the pharma industry. Now, as I hope I've made clear with this list, equation states can be extremely versatile. However, real difficulty comes with implementing them in general. Now, just to give you guys a quick history behind the different classes of equations of state, let us start with one hopefully everyone should be familiar with, the ideal gas equation, or Clapeyron equation, where all species are represented as infinitesimally small particles. It would take a few decades for van der Waals to come along with his famous equation, where we now begin to account for the excluded volume of species as well as interactions between particles. From here, our timeline branches, where one section of the thermodynamic community spent time making empirical improvements to the van der Waals equation, leading to the cubic equations of state, which have lost most of their physical interpretability of van der Waals equation. And parallel to this, another section of the community spent time improving the underlying theory of the van der Waals equation, culminating in the statistical associating fluid theory, which represents species as interacting chains with little association sites to mimic hydrogen bonding. Now, it is worth pointing out that along with these two other branches, high accuracy multi-parameter equations of state were also being developed. And another class of a thermodynamic model that doesn't really fall under the umbrella of an equation of state are the activity, lattice, and Cosmo-based models, which are restricted to modeling equilibrium properties of mixtures. Within Clapeyron, we support over 50 of these models, and I believe I can now say with confidence we support more models than most other open source implementations, where we cover the general cubics, Saft equations, activity quotient models, Cosmo-based models such as Cosmo-SAC, and these high accuracy multi-parameter equations of state. Now, with that being most of the engineering aspects of the way, I'll now give some brief computational details about our package. First, one question that we get asked a lot whenever we present this is why we decided to implement Clapeyron within Julia. Now, like a lot of other Julia enthusiasts, we were drawn in by the promise of C-like speeds, but with MATLAB and Python interpretability. We then quickly found a large and very friendly community with a wide range of packages and many high-performance non-native solvers and optimization libraries, some of which have been brought up in the last few talks here today. One aspect of Julia I'd like to bring up that isn't quite talked about as much is the extremely concise syntax arising from the support of Unicode characters. I've personally found it much easier to communicate with both experts and non-experts about my codes because of almost one-to-one mapping between mathematical expressions in papers, for example, and the implemented code that we have within Clapeyron. Even for these, which leads to some of the more concise implementations of quite advanced equations of state. Now, beyond the nice syntax, the Julia computing language has helped us address a few challenges with equation to state modeling. To summarize, most equations to state can essentially be simplified to a function that is dependent on the volume, temperature, and composition of our system, and the output of this function is what is known as the Helmholtz free energy. Now, this property alone is not very useful, and to get even useful information at a given set of conditions, such as pressure, temperature, and composition, we need to solve this optimization problem. Now, this equation here is the bane of every thermodynamicist's existence, where even in the simplest case, where we just have one phase with a single component, challenges can arise, where here, if we optimize with respect to the volume of our phase, we get the following equation where we must have equality of pressure. And this alone highlights one of the challenges of equation state modeling. For the equations to be useful at all, we must be able to differentiate them. And even beyond this, to obtain other useful properties, we need to take different and higher order derivatives. Now, as mentioned in the last talk, Julia has first class. Just to show you how it used to be done in some older packages, most of the people would derive these derivatives analytically. And these derivatives can get very messy very quickly, as these equations can be absurdly long. Now, of course, this approach can be quite tedious and prone to error, and has really acted as a barrier to entry for developers of equations to state. Now, as highlighted in previous talk, Julia has first-class support for automatic differentiation, where without going into too much detail, these methods allow to obtain numerically exact derivatives of arbitrary functions without having to do so analytically. This means that from our perspective at Clapeyron, we only need to code up the Helmholtz free energy, and the rest of the derivatives have been abstracted away thanks to AutoDiff, allowing us to obtain all thermodynamic properties for free. Beyond this, however, automatic differentiation has proved useful in our numerical methods, as having access to these higher order derivatives, such as Jacobians and Hessians, is very useful when using gradient-based algorithms. It also gives us access to other properties, which other packages never had access to because they depended on much higher order derivatives. One of these is the critical point of your species. Now, initially, we were a bit skeptical about using automatic differentiation for fear of a computational penalty that it might cost compared to analytical derivatives. However, when we benchmark our code compared to other similar packages, we realized that these concerns were unfounded, as our methods turned out to be much faster than even when compared with other compiled languages such as Rust and Fortran. So we were quite happy with this. The other challenge of equation state modeling relates to the solvers. Now, ideally, we'd only need one solver which works for all equations to state. However, certain equations have more optimal ways to solve the problems for certain properties. For example, for a generic equation, we need some sort of, to solve for the volume at a constant pressure, we will need to use some nonlinear iterative algorithm, as these functions can be quite unwieldy. However, for the cubic equation states, as their name implies, these can be rearranged to re-express a problem as a cubic polynomial, which can be solved for analytically. In other languages, the workaround for this would be to use object-oriented programming. In Julia, a different paradigm is used, known as multiple dispatch. To give an example of this, within Clapeyron, our equations must all fall under a type hierarchy, the head of which is the generic EOS model. We can then divide the model into different subtypes, such as cubic model, self-model, and activity, after which we define types specific to the equation as stated. Now, this allows us to write a generic and optimized method for our code, where the input type we can have the generic one which takes in any EOS model type, and we also have one that is specific for the cubic model which solves it analytically. Now, that is enough for the technical details. I will now showcase some of Clapeyron's service level features. Now, to make Clapeyron as accessible as possible for novice programmers, we have tried to keep the interface as simple as possible. To construct a model from which you can begin to use the solvers within Clapeyron, all you need to do is specify the equation state and the species name which you wish to model. Here I show an example with Redlich-Kong and Peng Robinson. Now, those more familiar with cubic equation states will know that when modeling a species like water, these cubics do quite terribly. However, within Clapeyron, we allow users to swap out pieces of their cubic equation state to try and improve the modeling. So, for example, if you wanted to model the saturation curve more accurately within a cubic, you would probably try to use an alpha function, which has been regressed specifically for water. Furthermore, if you wanted to capture the densities more accurately, you might use a volume translation method. Now, users can then trace the saturation curve using our solvers and then visualize the results, or they can see the impact of using their various modifications on the predicted properties. This is not limited to pure systems either. We can also use Clapeyron to model mixtures, for example, modeling the cryogenic separation of carbon monoxide and carbon dioxide. One might realize that the base Peng-Robinson method might not be so suitable, so you could swap out the alpha function with something like Boston-Mathias to model supercritical components more accurately. Alternatively, you might be tempted to use a different mixing rule, or perhaps you realize that this mixture is quite non-ideal, and as such, you'll need to use a predictive cubic method, such as VTPR, to try and model the binary interactions more accurately. From here, you can easily generate the results, such as this PXY diagram shown here, where we are able to evaluate the performance of the different models that we've proposed. And as I hope I'm making clear with the simplicity of this interface, one of the objectives of Clapeyron is to make it as easy as possible for engineers to focus on the science and evaluate the models, the evaluation of the models, without having to worry too much about the implementation. Now, one more binary mixture that might be quite relevant within the realm of carbon capture is the phase equilibrium between water and carbon dioxide. As shown here, the results obtained using a simple cubic such as Peng-Robinson are quite far from the more accurate predictions made by the higher accuracy SAF type equations, so CPA, PCSAF, and SAF-ERMI. Now, beyond vapor-liquid equilibria, Clapeyron is also able to obtain bulk properties, such as the isobaric heat capacity of here shown for pentane, or the Joule-Thomson coefficients shown here for carbon dioxide. This is possible for most bulk properties that engineers might be interested in. Clapeyron is also able to handle more complex phase equilibria. Shown here, we have two mixtures with the existence of a free phase equilibria. Typically, these phase diagrams would be quite complex to generate, as they involve both vapor-liquid and liquid-liquid phase equilibria. Thankfully, Clapeyron has support for both types of phase equilibrium. Clapeyron can also be used beyond simple binary mixtures. Here we show two PT isopleths, one for 4 components and one for 12, where both of these are liquefied natural gas systems. We are also able to model Ternary mixtures, where it would be a simple immiscibility curve, shown here with a water, oil, and alcohol system. And even more complex systems, where we have vapor-liquid equilibrium, liquid-liquid equilibrium, and free-phase equilibria. Now, in our latest update, we have also included support for solid-liquid equilibria, where we're able to model eutectic mixtures such as thymol and decanol shown here, and the solubility of pharmaceuticals such as ibuprofen within mixed solvents of water and ethanol, where we're able to model the regions where you have a pure liquid, solid-liquid equilibria, liquid-liquid, and free-phase equilibria as well. Now, this wide range of support for various properties has led to Clapeyron's adoption by various members of the thermodynamic modeling community, with some examples including works looking at tracing the Widom line of binary mixtures, solubility of pharmaceuticals, and within our group at Caltech, modeling the solubility of carbon dioxide within polymers. Recently, a group has used Clapeyron to model the immiscibility between water and PEG at various molecular weights, and it has been very exciting for us to see our package gradually get more and more attention within the literature. However, these are still just the service level features of Clapeyron. One aspect we have spent a great deal of time developing has been the customizability of this package, which comes in 3 forms. In the first instance, we allow users to input their own custom parameters. While most other packages would take their input parameters in the form of JSONs or XML, Here we decided to use Excel reasonable CSV files, where the structure we require for our parameters to be laid out in is very similar to how they would typically be presented within the literature. The hope here is that one could hypothetically simply copy and paste the tabulated values into Excel, save it as CSV, and from there simply specify the parameter location. And as long as these parameters are physical, they should be instantly compatible with all of our solvers. Furthermore, also more so a byproduct of Julia's multiple dispatch paradigm, users will also be able to define their own custom methods to obtain their own properties if these aren't available in Clapeyron. So one example shown here is how one would define the function for solvation free energy. And by using the Clapeyron architecture, where you can take models as an input, you should be able to use these methods for any other of the models available within Clapeyron. So here I showed how one might do so for PCF, SRK, and VTPR. The idea here is that Clapeyron could become a place to develop and benchmark new algorithms for evaluating thermodynamic properties such as flash algorithms or other iterative methods. Now, the last aspect we allow customizability for, and what we hope more users will take advantage of, is the development of custom models. Here, this is where users would want to try and implement their own equation state that isn't already available in Clapeyron. Users would only need to define the model parameters. So in the case of a PCF equation, you may need the molecular weight, the number of segments, the size of segments, and a few of the other interaction parameters. After this, you'll just need to define the model types, and then using our macro, all the internals administration required will be handled or be abstracted away. And here, the example I'm considering showing you guys is if you wanted to implement a variant of PCF as PCF. After this, users will only need to define the model's references, the location of their parameters, and any transformation that those parameters might need to be used in the equation of state. From here on, users will just need to find the expression for residual homosphere energy, and thanks to automatic differentiation, the rest of the derivatives are handled internally within Clapeyron. Now, so long as everything has been done correctly, the model will instantly be compatible with all our solvers within Clapeyron. The idea here is to try and really simplify the process for model development within the research community and try and make it easier for developers to make their equation available to the wider research audience. So while we weren't so confident that this capability would be used much, we were very, very excited to see that earlier on in this year, a group over at the DTU have used Clapeyron to implement their own thermodynamic models here to model water, and they refer to this approach as DAPT. They also have defined custom methods which allow them to use Clapeyron to study the association structure of water using different levels of theory. Other examples of this was actually done by myself, where I implemented a novel mixing rule in PCSAFT and which allowed for the integration of activity models to improve prediction of multi-component mixtures. And with that, I've summarized most of the capabilities that base Clapeyron offers. I'll now highlight some aspects which are currently under development, as well as some extensions of Clapeyron. Now, this section used to be quite a bit longer when I last presented on Clapeyron, as the package has now reached the point where we have implemented most of the features we initially set out to include. Now, the major outstanding feature that is missing is for electrolyte systems. This is something that is currently in active development, and we already have a basic implementation working, where I've personally used this to study the salt-induced immiscibility of water in acetonitrile using different salts. Nevertheless, Clapeyron is not the only package we have been working on. We have gradually been developing a whole Clapeyron modeling environment. The first of these is what we refer to as GC identifier. Now, the idea behind GC identifier is that there are some approaches referred to as group contribution models, which rather than using species-specific parameters, species are now assembled from constituent groups. Unfortunately, choosing how to assemble those groups can be a bit of a tedious process, as you have to manually define how many times a group occurs within a species. As such, the idea behind GC identifier was so that all that you would need to do is specify the name of your species, the groups you wish to assemble it from, and then this GC identifier package will spit out the groups that you need to use to model species, as well as their occurrence within the species. You can then feed this input into your generic, to your group contribution equation state, and then everything else will work as normal. This is compatible with all of our group contribution approaches in Clapeyron. Now, this package has proved to be quite useful, especially when doing molecular design, where one must iterate through many structures, repeating this operation multiple times. And this has definitely been useful in our own computer-aided molecular design, where we have to use machine learning techniques to try and propose novel structures. Now, one other package we've also been working on is thermoplots. Now, as the name implies, this package aims to optimize the generation of common figures. This is something that's helped me a lot personally in being able to implement and test models very quickly. Now, as an example, let's say you wanted to draw a saturation curve from multiple species. As I showed earlier, this might take about 20 lines or so. And using this package, this can be all brought down to just one line. This is hopefully going to be quite useful for novice programmers, where although they may not be familiar with how to plot figures within Julia or how to even use the solvers within Clapeyron, this will abstract away the entire process where they only need to call one function to plot their desired figures. We have also extended this to binary mixtures as well, where we can automatically generate PXY diagrams. These algorithms have gone quite sophisticated, where they can now recognize when different types of phase equilibrium are occurring, whether it be vapor-liquid, liquid-liquid, or free-phase equilibrium. Now, the last package I'll be talking about that we have worked on is what we are calling CDFT. This package aims to provide open source implementation of classical density functional theory. Now, for those unfamiliar with these methods, DFT can be used to obtain inhomogeneous properties such as surface and interfacial tensions, as well as absorption isotherms. And like everything else we do in Clapeyron, we've tried to keep the interface as simple as possible, where one would be able to calculate the surface tension with only a single command. Within my own research group here at Caltech, we have been using this package to design novel surfactants, where we can predict the interfacial tension between water and oil in the presence of surfactants. This has been quite exciting, as there are many packages out there that provide open source implementation of classical DFT, and we are very excited to see how this will be used by the more general research community. Now, while this has been a summary of things that we have developed within what we all just referred to as the Clapeyron environment, the last aspect I'd like to bring up is something that has arisen from the latest Julia update, where with Julia 1.9, extensions have become a very powerful and useful feature. This has allowed us to easily extend compatibility with other packages in Julia. One example has been our extension to the coolprop library, where we're now able to use the high accuracy equation states available inside coolprop within Clapeyron. Another interesting extension has been with Unitful, where users can now vary the unit system they use beyond the standard SI units which we use in Clapeyron. So for example, here one can specify bars, temperature, and masses, and then get the output units in either the default SI units or specify different outputs. We have also added extensions to measurement.jl, where users can now specify uncertainties in the model parameters. And these uncertainties will be automatically propagated through Clapeyron, allowing users to estimate the uncertainties of their output properties, as shown here for the heat capacity, where we can see that the uncertainties in your predicted properties can actually vary quite a bit as you change the temperature. Now, while these packages are examples of how to use external packages within Clapeyron, we are now looking to see potential applications of Clapeyron within other packages. Early examples include collaborations with Molly.jl, which is a molecular dynamics simulator built in pure Julia. There is also Fermi, which provides quantum chemistry methods. We also have a pair of students looking to use Clapeyron with Flux, where they're trying to develop to develop a neural network to predict thermodynamic properties. However, the extension we are most excited about and will likely be of most use to this audience has been with Jutil-Darcy. Now, for those unaware, Jutil-Darcy is a general-purpose media simulator developed by Olav Moyer for systems such as carbon dioxide sequestration or gas storage. Here I show a simple example of a simulation of a basic well provided within the package. Now, when it comes to modeling real systems in Jutil-Darcy, it uses its own package called multi-component flash for thermodynamic closure. This package currently only provides implementations for cubics. And over the past few weeks, we've made modifications to Clapeyron using the extensions to make it compatible with Jutil-Darcy, where one can now readily use most of the models we have built within Clapeyron inside Jutil-Darcy. Here I show an example of how one might do this, where all you need to do is build your equation state as you would do earlier on in the talk, and the rest of the Jutil package will work pretty much as it did before. And here I show an example of simulations where Clapeyron was used within an oil system where carbon dioxide is injected at the bottom of a well filled with water. We were very excited to see this, as it was the first example of Clapeyron being used within a process simulator such as Jutil-Darcy, and makes us very excited for the future of Clapeyron. Beyond that, the ability to make two packages compatible like this with limited effort is an aspect which is only really possible within Julia, and has reassured our decision to have implemented our package within this wonderful language. Overall, we have found Julia to have been an amazing platform for scientific computing. Clapeyron has now become a very mature and flexible library that is bringing together all equation to state modeling, and we are glad that it has helped remove the previous black box nature of equation states, making it accessible to expert and non-experts alike. I provided here the link for people who might be interested. And of course, I would like to give some very special thanks to my co-developers in Clapeyron. Andrés was the one responsible for making Jutil-Darcy compatible with Clapeyron and has put in a lot of work over the past weeks making that happen. And of course, some special thanks to some of the people who have supported this endeavor from the beginning. Thank you very much. I'm now open for questions.